All right. We'll start the next technical session momentarily. This is technical session 9, and it's around smart contracts. My name is Raja Jurdak from CSRO Australia. I'll be chairing the session. And in the session, we'll have 3 papers. And the first one is titled Probabilistic Smart Contracts Secure Randomness on the Blockchain. So the presenter for this paper is Amir Kafshtar Goharshadi. I hope I said your name okay.
Yes, perfect.
And Amir is a 4th-year PhD student in theoretical computer science at the Institute of Science and Technology in Austria. And his work is especially focused on applications in verification of smart contracts and cryptocurrency protocols. Finally. All right. Sorry for the delay, everyone. Over to you, Amir.
This is what being a computer scientist actually means, because not the theory about everything. My name is Amir Goharshadi, and I'm going to present this paper. This is actually a joint work with my advisor, Krishnendu Chatterjee, and Arash Purdamwani. So what I'm going to talk about is how to generate dependable random numbers on the blockchain. Now, you might think that, well, RANDAO exists, so the problem is solved, but here I will show you that actually RANDAO has some problems, and we have a better way of generating randomness on the blockchain. So first, why do we even need random numbers? This seems like a silly question, because we all know that probabilistic programs are... We all know that probabilistic programs are much more general than normal non-probabilistic programs, and there are many cases where we actually need randomness. So if you think of normal financial contracts in the real world, we have lotteries, we have gambling, we have all sorts of things that are inherently probabilistic. And if we need to implement these things as smart contracts, we actually need to have some source of randomness. Ideally, we would need something that can be implemented as a smart contract and provides randomness to other smart contracts. So I would like to continue this talk by a story about a lottery, but just a simple disclaimer, please don't sue me. This is fictional, not based on anything. Definitely not based on the Colorado lotteries. Okay, so here's the story. We have a famous celebrity called Ed, pictured here, who is rolling the raffle drum for a lottery, and he has to roll it 4 times so that we can find the winning number. And when he's doing this, in the second roll, the number 8 comes out, and he just says that he hates the number 8, it's his unlucky number, so he puts it back and rolls again. Is this cheating? Well, the answer is definitely yes, because it turns out that Ed had bought a lot of lottery tickets, like almost half of all the tickets, and he had bought exactly the tickets that did not have any 8 in them. So by doing this small redraw, he actually increased his chance of winning the lottery. So if we're going to create dependable random numbers, the first rule that we're going to have is a no redraw rule. So no one should be able to just cancel the result and ask for a new result. Okay. Next year, the organizers just ban redraws, but it turns out that Ed wins again, and after more deliberation, it turns out that he had actually bribed the person who made the lottery draw. So we get another rule. We shouldn't have any centralization. So no one gets to make the draw, no one gets to be the only one who draws the random numbers. This is a normal rule for blockchain applications, of course. Okay. The next year, the organizers invite 4 different celebrities and ask each of them to do one of the roles. But Ed is the last one, and he actually wins. And the reason he wins is that he can look into the numbers that were generated by the previous people and just generate a number that makes him win. So we need a concurrency rule, in the sense that everyone should draw their numbers at the same time, or in other words, at least before knowing what other people have drawn. Sorry. Okay, continuing this for another year, and this actually continued for like 14 times in Colorado, so it's realistic. So the next year, the organizers enforced concurrency by saying that everyone should draw at the same time and keep their ballots in their hand and then announce it one by one. But what happens is that when the first 3 celebrities announce their ballots, Ed just walks off and does not announce his. So they have to invite someone else to do the fourth draw, and Ed again wins. And here again we have this concept that people should be forced to announce what they have drawn. So there should be a penalty for this kind of behavior, for not announcing the random number. And this penalty should be at least as big as the lottery prize itself. Otherwise, Ed would always just walk away. Okay. But even if we solve that, there is another problem. If Ed buys all the tickets that end with, let's say, 33, then he can just draw 33 and win all the time. So we also have a rule of 1, which says that even if one participant is generating uniformly random numbers, then the overall output of the random number generation should be uniformly random. Okay. Finally, in the last year, what happens is that the organizers say that, okay, all of you create a complete number, and we just take the XOR of these numbers and say that that number wins. But turns out Ed just bribed everyone, so everyone colluded with him. So we need another rule. We need some sort of openness rule, saying that anyone who can pay the deposit can actually take part and create random numbers. So that's also a good reason for doing it on the blockchain. Okay, but then again, this story is going to continue forever. Next year, anyone who can pay the deposit can participate, but no one is willing to participate because we have to pay them reward to participate. Why else would they just hang their money for us? But even paying rewards is not enough. If you pay a reward to everyone for giving you some sort of random number, they might not really bother creating a random number. They might just give you 0 all the time. So we need some sort of incentive, not only for participation, but for actually giving out uniformly random inputs. So, based on these things, I would like to talk a bit more about how these incentives should work, and I actually want to kind of formalize this incentivization rule that I just mentioned. So, consider this game of submitting random numbers as a classic one-shot game with n players, where the players are the people who are submitting these random numbers. And let's look into some notions of equilibria that are standard in game theory. So we have Nash equilibrium. In a Nash equilibrium, each player has a strategy, and no player is willing to change their strategy, assuming that other players keep theirs. So the idea is that if all the other players keep their current strategy and I change, I will at least not gain anything. So Nash equilibria are the standard notion of stability in game theory, in the sense that if a game is in an equilibrium, no one is really willing to change. But the problem is that if you're trying to create random numbers on the blockchain, the players are kind of anonymous. They're taking part using only their public keys. So the n players are not actually n distinct players. Some of them might be controlled by the same person. So the idea of a rational player in a game doesn't really make sense here because they can collude, basically. So we also have the notion of strong Nash equilibrium, which we say that the game is in a strong Nash equilibrium if no set of players can collude so that all of them get better payoffs. But even this is not enough for blockchain games, because if I have 2 different accounts and I'm taking part in this game of random number generation using both of my accounts, I don't care if the payoff for one of them goes down, as long as the total payoff increases. So we need another notion of equilibrium, which is called quasi-strong Nash equilibrium, and it says that the game is in a quasi-strong Nash equilibrium if no set of players can collude so that their total payoff increases. And actually, quasi-strong is stronger than strong, but somehow people in the game theory community decided to call it quasi-strong. So this is the strongest notion of stability that we have. So if we can design a mechanism such that when people submit these random numbers, the only quasi-strong Nash equilibrium is that they submit truly uniformly random numbers, then we are actually incentivizing them to give us real random numbers. And this is exactly what we want to do. But before that, let me talk a little bit about the previous approaches that exist for creating random numbers on the blockchain. So one really bad approach is relying on the block hash or the block timestamp and using it as a seed for generating a pseudo-random number. The problem here is that just assume that Ed is the miner. When he mines the block, if he sees that he's losing the lottery, he can just redraw it. He can ignore his block. I mean, he loses his mining fees, but a lottery is worth much more than a mining fee for a block. Another approach that is being used is using an oracle. But then the oracle owner is basically the creator of the drum and can give us any number they want as the random number. The approach that is used much more widely is what RANDAO does, which is using commitment schemes. So in this approach, there are two phases. In the first phase, the participants can register, and for registering, they have to pay a deposit. And then they also have to commit to a choice of a random bit, B, or, well, generating a random bit or a random number is the same thing, basically, because we can generate several random bits. And they commit to it by submitting the hash of the bit B and some nonce that is private to them. And then when everyone commits, the revealing phase begins, and each participant has to reveal their nonce. Sorry. And, well, the generated random bit is, again, the XOR of all the submitted bits by all the participants. But the rewards for participants are dependent on whether they reveal their choice or not. If they don't reveal their choice correctly, their deposit would be confiscated. Otherwise, they get some reward. But again, this has the problem of not incentivizing the participants to submit actual random numbers. So if I take part in this scheme and only always submit 0, I get the same rewards as someone who is always truly submitting random numbers. But on the other hand, the problem is that we kind of depend on this assumption that there is at least one person who is submitting uniformly random numbers. Otherwise, our system is not really working. So we have an assumption that we are not incentivizing. And this is what we solve in this paper. So basically, our approach is to use the same commitment schemes, but instead of giving everyone a flat reward, we say let the reward depend on the submitted random bits. And we make it a game, basically, and make sure that the only quasi-strong equilibrium of this game is to submit uniformly random numbers. This incentivizes everyone to submit uniformly random numbers. So how does the game work? The game can have an arbitrary number of players. Let's say we have n players. So each player gives us a bit, 0 or 1. And for an even-numbered player, we interpret this bit as being either 0 or 2. And for an odd-numbered player, we interpret the bit to be either 1 or 3. And then let's say that player I plays SI. And what we do is that we simulate a mini-game between every pair of players. And the mini-game is illustrated here. Basically, if a player that has submitted 1 plays against a player that has submitted 0, the player that has played 1 gets 1 point, and the player that has submitted 0 loses 1 point. And it's basically a loop. If you submit your opponent's number plus 1, mod 4, you get 1 point. Otherwise, you get negative 1 point. And if you have the same parity, you basically get 0 points each. Now, it is... in the paper, we have a formal proof that the only quasi-strong Nash equilibrium of this game is for every player to play uniformly at random. So we take this game that has this nice property and plug it into commitment schemes. So our overall protocol, which we actually implemented as a Solidity smart contract, consists of these 6 steps. in the first step, another contract requests some random number and also sets the penalty for walking away and the reward for generating the random number. And then, just like the commitment schemes, participants can register in a given time frame. They have to give a deposit. They have to commit to the bit that they want to submit. And then they have to reveal it. And then the deposits are paid back to people who revealed the correct nonce and are confiscated from others. And then the contract plays this game and gives them rewards that are proportional to their score in the game. So everyone is incentivized to give us truly uniformly random numbers. And finally, the output is again the XOR of all the submitted bits. So my background is mostly on formal methods and verification. So in the paper, we actually formally define these rules that I mentioned here and prove that our protocol actually satisfies all of them. So we don't allow redraws. There is no centralization. The concurrency, penalty rule, rule of one, all of these things are satisfied. And the incentivization is due to the game. And finally, we also prove that our approach is safe against malicious miners, so they cannot interfere with it by block withholding or denial of service. And another thing that I don't have in my slides is that we actually did an evaluation of our approach, and on the Solidity platform, it can produce around 170 random bits per second. So the speed is not too great, but I think it's good enough for most applications. And that's it. I'm happy to answer any questions.
Hi, thank you for your talk. I'm just curious about the commitment schemes. It's well known that they are not resistant to the sabotage attacks when the last participant who is willing to, who is revealing his number after the first stage may just not reveal this number and sabotage the round. So I'm curious how you deal with this sabotage situation in your protocol.
So this is the penalty rule that we had. So let's say that we're using this random number for generating a winner for a lottery of, let's say, $2 million. So every participant has to put a deposit of $2 million, and if they don't reveal, they will lose that deposit. So they have no incentive of actually cheating and not revealing their final choice.
And is it realistic to put
It's realistic in the sense that if you want to create a random number for, let's say, a $2 million lottery, you can easily get 10 or 11 people who would give $2 million as a deposit if they can read the smart contract and see that they can get it back later on, given that they also get some reward for it. And the reward is also set by the person who is asking for the random number. So if I'm a lottery organizer, I would say that I give you $1,000 for putting your money here for, I don't know, 10 minutes. And that makes perfect sense.
Okay, so this is 10 or 11 participants. What if you have a million participants of the lottery? What will be the deposit? $5?
Yes, the idea is not that all the participants of the lottery have to participate in generating the random number. So when I say participants, I mean people who interact with this contract for generating random numbers so that they can get a reward. And these are completely independent of people that the random number is actually generated for.
Okay, thank you.
Hi. Yeah, thanks for the talk. So let's see if someone wants to obtain, let's say, a 4-bit random number through the smart contract, regardless whether it's a lottery or whatever. So if I request, I want to have a 4-bit random number, then what happens is that your smart contract will call for the volunteers who would deposit his money and generate his random bits according to the rule you describe. Then once the random numbers by storing those 4 random bits provided by those volunteers are delivered back to the caller of the smart contract routine. Am I understanding it right?
Right, yeah.
Then how much will be the delay in that case? Because
Well, you can almost set the delay yourself. So it depends on how long you let the phases for registration and revealing the nonces be. And there is a trade-off here. So the longer time you give for revealing the nonces, the less possible it is to do a denial of service attack on you. So you don't want to make it too fast. In practice, what we do is that we use the 6-block rule. So we gave 6 blocks for registration, 6 blocks for the nonces. Overall, it would be 13 blocks. And mining each block in Ethereum takes like 14 seconds. So you do the math, 13 times 14 seconds. So it's not super fast, but the good thing is that if you need 4 bits, you don't have to go through this sequentially. You can do it in parallel. So no matter how many bits you need, you can do all of them in, let's say, 14 blocks.
so in case if I want to, if these routines are implemented in the concrete language such as Solidity, then as a caller of this random number generator, once I call this function, assuming that I will not be getting the number, the random number I want immediately, then will that involve I as a caller set aside a space to which the eventual random number will be delivered by the smart contract, and after some time delay, that random number generator smart contract will come back and call my program to input whatever the random number generator into the space I have announced to the generator. Is this how it will work?
We can actually implement it like that, but our implementation right now is passive. So the way it works right now is that your contract has to call this and say that it wants a random number generated, and then 14 blocks later it has to call again and ask what's my random number.
I see. Yeah, thank you a lot.
All right, we'll leave it there in the interest of time. Let's please thank our speaker. So, as our next speaker sets up, the next paper is Verifiable Smart Contract Portability. It's going to be presented by Martin Westerkamp, who's graduated from the University of Munster in 2017. He focused on information systems development, business intelligence, and model-driven software development. He's currently doing his PhD at TU Berlin on blockchain interoperability.
Right. Thanks for the introduction. Yeah, today I will present to you verifiable smart contract portability, which will allow you to migrate smart contracts between EVM-compatible blockchains. So first of all, why do we need this at all? So when developing decentralized applications, we can observe an architecture where we have 3 layers. On the base layer, we have the blockchain itself, and then on top of that, we have the smart contract that consists of a logic and a state. And then on the 3rd layer, we have an access layer that is there for displaying, or itself can have some business logic again. And while this access layer is quite loosely coupled to the smart contract, so we can easily change to another node, for instance, the smart contract will be linked to the blockchain forever. So once we have deployed that smart contract to the blockchain, it will stay there forever. And this mitigates the initial goal of using a smart contract, right? Because the initial goal of using smart contracts was to not have any lock-in effects and not to have one single point of failure. And this single point of failure could become actually our blockchain now. And this is especially the case because we inherit all the characteristics of the host blockchain. So we inherit the security characteristics, and if over time there is less incentives for miners, for instance, in the proof of work, to mine, then also the overall hash power will decrease and the security will decrease as well. Also, we may have vulnerabilities in the executing client implementations, and performance-wise, we also inherit this performance throughput characteristics and so on for our smart contract that over time may not really suit our needs anymore. Furthermore, we have observed that developing smart contracts can be quite tedious, so we have just heard an interesting talk about that. This is leveraged actually by the fact that we use libraries on Ethereum, so our smart contracts are not isolated, and these libraries may be vulnerable again. So in the Parity multisig wallet, for instance, we were relying on such a vulnerable library, and this can have serious consequences. And while we cannot bring back those funds, we can fork smart contracts at a given point in time and then bring back that state that has been present before. And lastly, over the life cycle of a smart contract, we may have varying or changing external requirements. So such requirements could, for example, create the need for changing from a permissionless to a permissioned blockchain, or also we could just have a new blockchain that is better suited for our given use case. So how would this look like? So our target is actually to maintain the smart contract together with this logic and the state and migrate it to another blockchain while not putting any new trust requirements in this executing entity. So this entity in the middle here that is performing the migration should not be trusted, and we achieve this by performing or by delivering full verifiability. So every participant who's interested in that smart contract can then later on verify the validity of that migration. So when migrating smart contracts, of course, we need a common execution ground. And we have observed that nowadays many blockchain implementations actually implement the EVM. So we have Qtum, we have Ethereum, Quorum, Hyperledger Bureau, Fabric, and Sawtooth that have some sorts of implementations of the EVM so they can execute that EVM bytecode. And this also provides a range of blockchain variations, so permissionless, permission, public, private blockchains, and also various different consensus protocols. So as a small reminder, when we develop smart contracts, we usually have a high-level language like Solidity or Viper, and then we compile this to bytecode, and this actual bytecode consists of a preamble that sets some memory pointer in the beginning, then a constructor that sets the initial state, and in the end we have code copy instructions that copies the actual contract code that maintains on the blockchain. And only that contract code maintains on the blockchain, and all the other parts are executed only during the deploying transaction. And as you may all know, of course, states in Ethereum are kept in Merkle trees, so every single smart contract has its own Merkle tree. And here we have an example with 3 different variables, and each variable is stored in or linked to a key. And so we have the keys 1, 0, and 22. And when changing value 0 from 5 to 6, only that value changes. The rest of the tree remains. Well, actually the root changes as well, so we can use this characteristic to compare if any change has been made. And we will use this characteristic later on to provide this verifiability, so we can just check the roots of the storage to be sure that nothing has been tampered with. So now you may think to yourself, why don't we just retrieve this Merkle tree then from the database? And the issue here is that we don't actually know the keys because we have mappings, first of all, so we don't know the keys of those mappings. And also it was a design decision in Ethereum to hash keys. And this was done because otherwise we could, like an attacker could just build arbitrary long Merkle trees and by this provide a lot of overhead for nodes and create DOS attacks on those nodes. So by hashing those keys, those trees will be kind of balanced. So how does this work altogether? So here we have an example of the entire workflow. In the beginning, we have Alice who deploys a smart contract with only a single variable a here, and in the constructor a is set to 2, and in the second step Bob then sets a to 5. Now Carol comes in, she has nothing to do with that smart contract, so she doesn't have to be the owner, she doesn't even have to know the actual high-level code, but she wants to migrate that smart contract, fork it onto another chain. And she does so by, first of all, retrieving the bytecode, which is visible for everyone participating in that blockchain, and secondly, she has to retrieve all those transactions that have ever been sent to that contract. So she has two options here. First of all, she could use an external database that links all transactions that had ever been sent on the blockchain to a target and use that database for retrieving those transactions, which will be quite fast. Or if she doesn't have that database, she could just go through the entire blockchain from the deployment transaction to retrieve all those transactions. And after having collected all those transactions, they will be replayed locally on her own device. And by doing so sequentially, she will obtain the final state. So each transaction is replayed, and the change for each key is observed, the change of the value and new values that have been set. It is to be mentioned that this won't be executed on the target chain, but only locally. And after having retrieved all those values, they will be used for constructing a new deploying transaction. And this is done only in bytecode, so we don't need any high-level code, don't need any access to that. And as explained before, in the beginning we have the preamble, and then in the constructor, instead of the original constructor of that smart contract, we now set the current state, and so we just have those push and set and store bytecode operations here. And afterwards, we have those code copy instructions and the contract code. This entire bytecode is then deployed to the target chain and can be validated by everyone afterwards. Like Dave here, he can now check the state root, and on both contracts it has been 1337. And he can also just use the contract as he would use it on chain A, and can observe by using the getter function that A now is 5. So for simple use cases, this works very well, but of course, smart contracts grow over time, so the state grows over time. And this may lead to a situation where we have a state that is too large to be deployed in a single transaction because it would exceed the actual block limit of the target chain. And as we want to be able to verify the state and the logic, we don't just add a new function that has keeps track of some migration phase, but we split the contract into several contracts to remain this verifiability. So now we have 3 different kinds of contracts. We have the logic contract, we have the proxy contract, and the initialization contract. And the initialization contract is only present during the initialization phase. The proxy contract keeps the state, and the logic contract keeps the bytecode that was in the original smart contract. So now when migrating, Alice first of all deploys all those 3 contracts, and then she uses the initialization contract for setting the state, and the initialization contract itself calls the proxy contract, and here again the setState function, but the setState function in the proxy contract checks who is calling it, and only this initialization contract is authorized to do this call. So after the migration is finished, this initialization contract is being destroyed, so it cannot be changed or tampered with afterwards. And this proxy contract actually implements 2 functions. First of all, this setState function and a fallback function. And fallback functions in Ethereum are called every time the function signature is unknown. So now when Bob calls the setA function here on the proxy contract, this is actually unknown. So the fallback function is called and initiates a delegate call to the logic contract. And delegate calls operate on the state of the calling contract. So while the logic's being executed on the logic contract, the state is used from the proxy contract. So now we have a situation where we can migrate over multiple blocks, we can spread the migration part, and also we can still migrate the state because it's untouched in the proxy contract, and we have a verifiable logic in the logic contract. So one more issue is, of course, we may have dependencies. So as said, smart contracts are not isolated, but they may rely on other smart contracts. They may use libraries, inherit, or also just have variable references. So those references can be variable, so set in the state, or hard-coded. And we have to obtain those because otherwise, of course, we don't have the full functionality anymore potentially. So we do so by going through all those values we have obtained before and checking for any addresses in there. And then we check on the source chain if those addresses were externally owned accounts or if they were smart contracts. And if they were smart contracts, we migrate those contracts recursively. So we kind of have a tree of smart contracts that potentially have to be migrated. And after having them migrated, we have to exchange, of course, the addresses in the calling contracts. And the same is true for the bytecode, but here we use the Mithril an analysis tool for obtaining those relationships and then also deploying them recursively. So to check the applicability and the if we can really do what we promised, we use one of the most used kinds of smart contracts, so the ERC20 contract. And we have chosen some random contract from the main chain, which has had 3,179 transactions at that time. And we want to port this contract to a private chain. So in this case, we retrieved all these transactions from an external database we have built before, and we use our tool to migrate that contract. So we have an open source tool that you can also check out on GitHub. You will see the link later. And so here the tool is used to, first of all, replay all these transactions. And this can be done together with Geth or Parity or any other node that supports debug, the debug mode. So after having replayed all those transactions, we have obtained 759 key value pairs that have to be migrated. And by doing this simple calculation here, because setting a storage key or a value costs about 20,000 gas, which is now more than 15 million gas, it exceeds the block size limit of 8 million gas currently on Ethereum. And because of this, our tool detects the situation automatically and splits it, as explained before, into 3 smart contracts. And we could observe and could verify that the state and the logic were valid and were equal on both chains. So one drawback we observed here was that we have additional gas costs because of this delegate call from the proxy contract to the logic contract. So each delegate call causes additional costs of about 956 gas here. And not particular in this contract, but generally there's a potential vulnerability because the contract that holds the logic has no state, but can be called by anyone, of course, changing the state and triggering now uncalled self-destruct instructions. So before migrating, we would have to check using Mithril, for example, for such unchecked conditions. In addition, we have created an own smart contract that has some relations, so it's not isolated, but it has, first of all, references in the state, but also in the bytecode. And our tool could observe all those references and migrate them recursively. So it was changing these target addresses than in the actual code that was obtained before. Here again, one drawback is that the verifiability is mitigated a little because we cannot just easily check the root anymore because we have changed now some storage values, right? So what we have to do is we have to build a a library kind of which addresses have been changed, and then iteratively again or recursively we have to verify those smart contracts as well, and all the other values as well. So there are some challenges, and of course for proof of work chains, those chains may fork in the future, or they may fork all the time, and we may do a migration on a fork and also the validation. So we may assume that we are operating on a valid smart contract, but this may not be the case necessarily, of course. And we have assumed that the same address pattern is available on the target chain for the source chain. If this is not the case, then we have to have some migration phase that links those addresses and allows us to claim them, like in ICOs with EOS, for instance. And in the future, I think one interesting topic is chain relays. So we can just validate some block headers, and then we can create Merkle proofs to prove that we have exactly the same state in this migrated contract without requiring external validation. One downside is native cryptocurrency, of course. We cannot just migrate it as easily. And one solution may be Cosmos and Polkadot in the future, but then we would have to have some ownership of that source contract, and it's not a fork like currently. Events, additionally, are linked not only to the contract itself, but they are rather linked to the block, and we cannot migrate them because they are historic. So one solution would be to have a middleware that allows us to forward requests depending on the age of the block. So in conclusion, we have created a solution that allows us to migrate smart contracts between EVM-compatible blockchains, including the state and the bytecode. We don't put any new trust assumptions because we can validate the entire process externally, and we have high flexibility because we can port a whole range of smart contracts, including those with references and those with large states. And we have created an open source tool that you can check out here on GitHub under this link, and you're welcome to test it and, of course, to contribute. So, thank you very much, and I'm looking forward for your questions.
All right, let's thank our speaker again. So our final speaker is Eric Wagner, who's a master's student at RWTH Aachen University with a focus on communication and distributed systems. And he, with his fellow students, he kickstarted Smart Judge, the lightweight framework for conditional dispute resolution. And his talk will be talking about that. His talk is titled Dispute Resolution for Smart Contract-Based Two-Party Protocols.
Okay, so now I can start. So first I would like to thank the other people at my chair who helped to realize this work. And let me start with a short introduction. So how we motivated our problem. So we looked at hash time locked contracts for atomic swaps, and what we see there is that we use this cryptographic guarantee all the time. But if we create incentives for users to be honest, we maybe can eliminate this need if we have some fallback method in case that some people are really dishonest. So this does not work. This doesn't work either.
Maybe try now.
Okay, so I have to do it like this. So our motivation comes from the real world. So here we have judges and a really expensive legal system. So if we really have to go to court, this can be really expensive. But this also results in the case where most people are honest, because otherwise they would be punished and they have no incentive to be dishonest. And on the blockchain, we have, again, expensive computations, but then we can maybe use this punishment to keep users honest. So our contribution is first a framework to, so maybe I have to say this results in a conditional dispute resolution, which has been done multiple times, and we have also heard at conference about this. But we want to generalize this idea for two-party protocols. So the first part of the talk is this framework, and then we looked at two use cases. The first being the fair exchange of digital files. So again, this has also been discussed at the conference. So the motivation, at least, for this problem. And we used the protocol FairSwap, which was presented last year. And we integrated it into our framework to see if it's really a framework that's usable by other solutions. And then lastly, we looked at the atomic swap of cryptocurrencies. And here we always have this full protection, and we want to see, is it possible to do this with conditional dispute resolutions? And we actually see that we are less expensive, and we have some benefits when it comes to privacy. So let's take an overview. So we have Alice and Bob who want to participate in some kind of two-party protocol. So let's say Alice wants to pay Bob for some service. And then what we actually want to do, we have this mediator, a smart contract on the Ethereum blockchain. And we want that if both parties remain honest, they can really cheaply and easily communicate with this mediator. And that all only in case that it comes to dispute, we have to rely on the verifier to really decide, okay, who was dishonest and who wasn't. We want to be extensible, so anybody can really deploy new verifiers. Then it's up to Alice and Bob or some trusted other party to decide which verifier are really correct for the use case that both parties want to do. And then, this results in the case that if both parties remain honest, we only have to communicate with this mediator, and only otherwise we have to fall back on our specific use case. And this also lets us be confidential about the terms of this agreement, as long as it does not come to a dispute. So if you look a bit more in detail at how the honest interaction would work, so we have Alice and Bob, and they off-chain negotiate some agreement. So they determine which verifier will be used in case of a disagreement, and then how this verifier would be initiated and what Alice is going to pay. And then the first step on-chain is that Alice initializes this agreement, and we just store the hash of the agreement. So this lets us protect the integrity of the data, but does not reveal really the agreement between both parties. And then, Alice escrows her payment and makes some security deposit. And then afterward, just Bob accepts this, and then we have this, off-chain fulfillment of the agreement. Here we can really save the cost because we do not have any costs related to the blockchain. And then this interaction has to generate this second witness somehow that can be used to verify in case that it comes to dispute. And then lastly, at least for an honest case, Alice just says, okay, everything worked correctly, Bob is being paid, and both get their deposit back, and we free up the storage, so we can really be cheap. So this results in now, we checked the price yesterday, and it was 29 cents for this interaction in case for honest parties, despite now the Ethereum price and gas costs rising again. And then we have to look, okay, how can this be cheated, and what methods do we use to really make this secure? So the first thing is that Bob can just not react after Alice initiated the agreement. In that case, we just have to allow Alice to cancel an agreement. And this also has the nice property that both parties commit at the same time, which is nice, as we will see later. And then, during the execution of the protocol, we have to use timeouts. So we force that the protocol is advanced, and if some parties goes offline, we just say, yeah, this was the dishonest party, and we give the money back to the honest party that's still online. And only then, in case it's come to an active disagreement between both parties, we rely on this verifier that was negotiated earlier. And only then we reveal the agreement and try to resolve the problem on the blockchain. So the first use case was already motivated here at the conference. So we have Bob with some file, and Alice wants to pay for it, but nobody wants to go first, because then the other person can just disappear and run away with the money, for example. So last year there was this solution proposed. So basically, in a nutshell, what they do is Bob first sends encrypted data to Alice, and then Alice can initialize this on the blockchain by uploading the Merkle tree root of the encrypted data and of the decrypted data she expects from Bob. And then Bob can upload the key, and this protocol results in either Alice having the file she wants, or she has a proof that she did not actually receive the correct file and can use this to get her money back. And we integrated this into our framework, and we just had to adapt the interface. So this was nice because it really showed that we really built a framework that can be used for other use cases. And then we built this additional abstraction layer on top of this protocol, because they already use conditional dispute resolution. But we still see, because we are really minimizing the interaction, that we can reduce cost by 22%. And what you have additionally is this confidentiality for the trade, because for honest parties, we do not reveal that this exchange of data is happening in contrast to the original protocol. And then our second use case, so the initial motivation, was this of the hash time lock contracts, because we have seen multiple times that the centralized exchanges cannot be trusted, but still we want to be able to interact with other blockchains and transfer our money to use other applications. So typically this is done with hash time lock contracts, and we have already seen this at the conference. So basically, Alice knows the secret, and she makes this payment in Ether to Bob, such that he only can get his Ether back if he reveals the secret, but he doesn't have it at this moment. And then Bob sends his Bitcoins in the same manner, and now Alice can reveal the secret, and then Bob also knows the secret and can get his Ether. So this has some potential for improvement. So the first is the cost. So we have this cryptographic hash that we use to link both transactions, and we wanted to see if we can remove some costs by removing the necessity for this cryptography. And then we have also the problem of fairness. So Alice has the power to reveal the hash or not reveal the pre-image of the hash, or not reveal it. And so she can look at the market rate, how the price is fluctuating, and then can decide, I want to go through the exchange, I do not want. And if we have long timeouts, so we can really profit from this. And then the third point is that we have this privacy issue, because we have this hash on both chains, so we can really easily link the addresses of both parties across the chain, and further make it easier to de-anonymize people. And then the last point is the extensibility, so both blockchains have to support this construct with a common hash function. So how do we want to do it with our framework? So Alice is going to ask for a payment for Bob, and then Bob is accepting that he wants to do this exchange. And then we have Bob transferring his Bitcoins, and then Alice can just release the Ether in the good case. And if one party says, there's something going wrong right now, we can initialize this dispute and decide, okay, who wasn't doing what he was supposed to. And here we have actually to verify that this Bitcoin transaction happened and is on the Ethereum blockchain. So Ethereum cannot interact with Bitcoin directly, so we have to do this somehow compactly so that we do not blow up costs. So we have this first witness that was created at the start of the agreement and agreed on by both parties. So here we just store how much should be transferred and where, also the address of Alice. And then we also negotiate a Bitcoin block hash that both parties say, okay, this is really in the chain and we agree on this. And then we have the second witness, which can be uploaded by Bob. And so that's his claim to the block hashes where the transaction is actually in the blockchain. And then Alice can say, okay, I do see these block hashes, but I do not see the transaction in any of them. So we can just use this simple payment verification for this one block and prove either the transaction is in it or not. And otherwise, what we can do, we can make a binary search for really to narrow down the block where Alice still agrees, and then the next block where Bob claims some block hash that Alice does not really agree with. And from here we can then just say, okay, Bob, Alice does not agree that this is an actual Bitcoin block, so just upload the block headers to verify that this proof of work exists. And we decide now to make 7 block headers that should be uploaded to prove that Bob did not just cheat just created one block by himself, but that is actually the real blocks from the Bitcoin blockchain. And then this verification process, in the worst case, we have costs of $2.75. So that's for the verification if a transaction is in the Bitcoin chain over the span of 2 weeks. So then we can look at the price. So here on the top graph, we see our approach in blue and the HTLC-based approach in orange. And we just use the Bitcoin Improvement Protocol 199 as the implementation for hash-time contracts on Bitcoin, and then the altcoin.io implementation for Ethereum to determine the prices. And then we see that we are approximately 50% cheaper, and this is fluctuating based on how Bitcoin prices and Ethereum prices are compared to each other. But even if Ethereum really gets stronger than Bitcoin, we still remain cheaper. And then, so how do we improve upon hash-time contracts? So first, we have these expenses that we can reduce. Then in terms of fairness, so we have both parties committing at the same time, how I said earlier. So we do not have Alice who has the power to decide later on if she wants to go through with the exchange or not. Then we have this confidentiality. So for honest users, we don't have to reveal the agreement, and we just have a standard Bitcoin transaction on the Bitcoin chain. And this makes it not possible to link the accounts, at least not easily. So, and then extensibility, that is really future work. So in theory, you can verify every blockchain, but it gets maybe really difficult if you do not have natively supported hash functions like SHA that is used in Bitcoin. So here we have to look at how applicable is this approach for interconnecting other blockchains also. So that's my talk. So you can check out our code. We have it on GitHub. And then we have seen this framework for conditional dispute resolution. And then we have seen 2 use cases. So the first is the trading of digital goods, where we can improve upon a protocol that already uses conditional dispute resolution by remaining confidential and reducing costs by 22%. And then for atomic swaps, we are fairer, we remain confidential, and we are cheaper by, at least at the moment, approximately 50%. So that's it for me, and I'm happy to take questions.
Questions from the audience? So you demonstrated that use cases with mainly digital goods. What are your thoughts on how smart judge could apply for physical goods and dispute resolution there?
So you have to somehow verify it if you want to be if you want this to be really trusted, but you also can use probably oracles or something like that. Yeah, if you do not have really an easy way to connect with the physical world. So we shortly discussed in the paper the use of tamper-proof sensors for some of these use cases, but that's really still some way off to use. And yeah, so it's probably possible to some extent. You maybe not have the full trust at the moment, and then, yeah, but it's potential there for future work.
All right, thank you. Other questions?
Do you foresee a protocol with multiple routes of adjudication in case of a dispute? And do you also think you can use this system to essentially report and agree on information on the blockchain? Like about the correctness of information on the blockchain? Like an oracle, like, which relates to what I've been working on.
So you could use an oracle as verifier in this case, and then have really the fallback of the oracle in case that Alice and Bob disagrees on. So is that what you mean? Okay. Yeah, so you can have this oracle, so then the trust, well, we cannot really prove the correctness of the oracle like we can for these use cases, but yeah, if you trust the oracle that's implemented in a way that's really decentralized, sure, you can use it. And then you can have much more use cases that we really can. Yeah.
Are you familiar with TrueBit?
Yeah. So we have discussed it as related work. So we can really, this interaction and the interactive verification is what we can do, what TrueBit cannot do, and then.
Correct. That's where I was going.
Yeah. So what maybe.
So, go ahead.
What maybe would be interesting is to have a TrueBit virtual machine as a verifier for this, and then you can have, yeah, basically you do not have the overhead of initializing TrueBit for honest parties, but we still can fall back on it for dishonest parties, and then you have some overhead, but not too much.
Okay, thank you.
Any final questions? All right, let's thank our speaker again.